Welcome all of you to this video lecture series on computational fluid dynamics, development, application analysis. This lecture 10 is on governing equations and engineering parameters, which corresponds to the topic 2, essentials for computational fluid dynamics. This topic corresponds to the chapter 3 of the companion book, the essentials of fluid dynamics and heat transfer for CFD. This lecture is the last lecture corresponding to the essentials of fluid dynamics and heat transfer for CFD. So this lecture is on governing equations and engineering parameters. In the previous lecture, I had presented the essential concepts of fluid dynamics and heat transfer, starting with physical laws, where I had presented mass, momentum, and energy conservation laws, and the Fourier law of heat conduction in stress-strain rate relationship as the subsidiary laws. After presenting the physical laws, the diffusion and advection are presented as the transport mechanism for the momentum and energy transport. In the last lecture, the initial and boundary condition, which acts as a jury to any fluid dynamics problem and dictate the solutions, are presented. Finally, the last essential concepts of fluid dynamics heat transfer to learn CFD is presented in this lecture, which corresponds to governing and engineering parameters. Whenever you study a fluid dynamics problem or any problem, there are certain input parameters and there are certain output parameters. So these governing parameters are the input parameters and engineering parameters are the output parameters corresponding to a fluid dynamics problem. The definition of these parameters are: governing parameters are the input parameters that govern or affect the results in fluid dynamics. Such as, to give an example, if you consider flow across a car, then the speed with which car is moving, or the dimension of the car, or the fluid in which the car is moving. These are the parameters on which that govern the results that may be corresponding to the flow field near to the surface of the car, or the drag force which acts on the surface of the car. So the speed of the car, the geometrical dimensions, and the fluid in which it is moving. These are the input parameters that govern or affect the result in fluid dynamics. Like if you change the speed of the car, the result, the flow near to the surface of the car, as well as the drag force will change. Engineering parameters are defined as the output parameters that are of interest to engineers, as this parameter lead to an increase in the cost or affect an efficient operation of an engineering system. Again, if we consider that example of flow across a car, then the output parameter, that the fluid dynamic output parameter which we are interested in, is the drag force. And the drag force lead to an increase in the petrol consumption, fuel consumption, which increases the maintenance cost. And if the drag force is large, then you have a low fuel efficiency. So it affects the efficient operation of the car as an engineering system. So this lecture is focused on input and output parameter corresponding to a fluid dynamics problem. Now there are three types of governing parameter. As I mentioned, thermophysical property, the fluid on which is considered for a fluid dynamic problem, governs the solution. Along with it, whenever you solve a fluid mechanics problem, there is an interaction of a fluid flow with a solid. Like for flow across a car, the fluid is interacting with the surface of the car. If you consider flow in a pipe, the flow inside the pipe is interacting with the surface of the pipe. And the geometrical parameter, like for flow in a pipe, the diameter of the pipe, the length of the pipe, this govern the solution. For flow across a car, the dimension of the car affects the solution. So along with the thermophysical property, the geometrical parameter is another type of governing parameter. Other than this, there are certain boundary condition related flow parameters, like for flow in a pipe, the velocity at the inlet of the pipe is the boundary condition related input. And for flow across a car, the velocity with which, the speed with which the car is moving is one of the boundary conditions which govern the solutions. These are the three types of boundary conditions. These are the three types of governing parameters. Initial condition is also a governing parameter for a transient or unsteady state problem. If you are interested in steady state solution, for most of the problems, the steady state solution is independent of initial conditions. But if you are interested in, if you are bringing a fluid dynamic from initial condition to the steady state, which is called as transient results, or if a problem reaches to an unsteady solution, which is varying with respect to time, then for this transient and unsteady results, initial condition is a governing parameter, other than these three types of governing parameters. So the last slide I had presented the governing parameters, which are input parameters, which depends on the thermophysical property, geometrical parameters, and the boundary condition. I would also like to mention the using this governing parameters, most of the time whether we do an experiment or computation, using this governing parameters, we try to reduce the number of input parameters by using a concept of non-dimensionalization. For any study which we are doing, we want to reduce the number of input parameters, and we also want to claim the results for wide range of operating conditions. Like, to give you an example, if you consider flow across a cylinder, the results for flow across a cylinder depends on the fluid thermophysical property of the fluid. It depends on the geometrical parameters such as diameter of the cylinder. It depends on the boundary condition related flow parameter, like what is the free stream velocity. Whenever we present the results for this problem numerically or experimentally, instead of, let us suppose in a fluid flow problem, you have density and dynamic viscosity as two parameters, the diameter of the cylinder as the third parameter, and the inlet free stream velocity as the fourth parameter. So there are four input parameters which you have to vary for that problem. However, if you define this problem in a non-dimensional form, you can take the combination of density, dynamic viscosity, diameter of the cylinder, and the free stream velocity, and use a single parameter which is called as Reynolds. So instead of any study that you are doing, if you have four different knobs or four different input parameters, then you have a much more challenging situation to do a comprehensive study, as compared to a situation where you have only one parameter, that's a non-dimensional parameter, such as a Reynolds number, where you can do the study much more easily. So this way, the non-dimensionalization comes as a great help in reducing the number of input parameters in any computer simulations. After the input parameter, the engineering parameters which are calculated, mostly these parameters are calculated at the surface or boundary of a solid for an external or an internal flow problem. Let us consider flow across a car, which is an external flow problem. So if you want to calculate the drag force is calculated. So the parameter is drag force. It is calculated at the surface or boundary of the car. This is calculated by calculating the viscous forces and pressure force which act at the surface of the car, and we do the surface integration of this pressure and viscous forces at the surface of the car. Whereas if you consider flow across an aeroplane, similarly we consider the variation of pressure and the viscous forces on the surface of the car, and then calculate the lift force. If you consider flow in a pipe, we can calculate the pressure drop per flow in a pipe by calculating the wall shear stress or the shear force on the surface of the pipe. So in a pipe, we do the surface integration of the viscous stresses at the surface of the pipe. Whereas in case of an external flow, a car or an airplane, we consider the viscous along as well as the pressure forces to calculate the lift and drag force. So since this output parameter involves the calculation of the parameter at the surface, like for flow across on a car, the surface is the surface of the car, and for flow across an airplane, it's the surface of the airplane. Now, this is the surface integral which is used, this is the expression for surface integral which is used to calculate the drag force. This is a cyclic integral because we calculate this forces, fluid dynamic forces, drag force as well as lift force by considering the pressure and viscous forces all over the surface of the car. The complete surface is considered, so that's why it has been shown as a cyclic integral. I will take an example problem for flow across an inclined plane to discuss this in much more detail, where the integrand which you see is basically sigma is the total stress which corresponds to pressure as well as the viscous stress, and n is the unit vector, unit normal vector of the surface. However, if you consider the surface of the car, the surface is a curved surface. So if you take the various points on the surface of the car, the direction of the unit normal vector will vary. So the integrand here is a vector term because it's a product of the second order stress is a second order tensor with a normal unit vector, and I had presented in my earlier lecture that the dot product of a second order tensor with a unit vector leads to a vector. And if you take the dot product of x component by taking the dot product with I unit vector, you have obtained the x component of that vector, which is called as drag force, and the y component is called as lift force. Whereas in a heat transfer problem, the engineering parameter is rate of heat transfer. Now, to calculate the rate of heat transfer, we take the dot product of the heat flux as a vector with a unit normal vector. This note that this unit normal vector is corresponding to the surface, and with this we obtain the heat flux and we take its surface integral. Now this n dot sigma is the operation is presented here for flow across an inclined plane. Let me explain the cyclic integral and what is this n, considering an example for flow across an inclined. This is a flat plate which is inclined, consisting of 4 surfaces, and the unit normal vector are as shown here. This is the unit normal vector. These are the outward normals, n1. This is n2. This is n3, and this is n4. And we are considering a free stream flow across this inclined flat plate. Now for this case, I am showing you the expression, this n dot sigma, for one of the surface. It could be a top or bottom or left or right, where this unit normal vector in a 2D Cartesian coordinate system is expressed here as AI plus BJ, and it is a dot product with a total stress. Now when you say total stress, you have pressure as well as the viscous stresses denoted by sigma xx, sigma yy. These are the normal viscous stresses, and sigma xy and sigma yx is the shear viscous stresses. Now when you take the dot product, the dot product of a vector and the second order tensor is a vector where the x component corresponds to the first column shown here. So you get A multiplied by this element and B sigma yx. This is the first component. In the second component, and y component is given by the second column. So the operation involves A sigma xy plus B into minus P plus sigma y by as shown here. And when you take, so this is the n dot sigma for one of the surface. Similarly, you do for the second, third, and fourth, and then you do the cyclic integral represented by summation of all the four surfaces. So this is the n dot sigma, and when you take a dot product of this n dot sigma is a vector, and when you take dot product with I, you get this x component which is given by this drag force. And there is a mistake here. This should be FL. This is the lift force. Let me correct it. This is FL. This FL is equals to the y component as shown here. So n dot sigma dot j is given by this, and n dot sigma n dot q, n is ai plus bj as shown here, and q is qxi plus qyj. So when you take the dot product, you get the cyclic integral as shown here. Here, one thing to note also is that this sigma, this viscous stresses, sigma xx is equals to 2 mu del u by del x, sigma yy is equals to 2 mu del v by del y, and sigma x pi is equals to sigma yx is equals to mu del u by del y plus del v by del x. So all these are viscous stresses. All of them are involving the dynamic viscosity along with the velocity gradients. So that was about the governing parameters and the engineering parameters. They were presented in dimensional forms. However, as I mentioned earlier, in any experimental or computational study, we prefer to present our result in a non-dimensional form. So as shown here, experimental as well as numerical results are presented in a non-dimensional form, since they are applicable to various fluid and large range of length and velocity scale. When you do an experiment, while doing the experiment, you have to take a particular fluid, a particular geometrical dimension. So that way, the experiment is always dimensional in nature. However, when you are doing a computational simulation, you have the luxury and freedom that you can set up your computer program in such a way that you can do simulations, computer simulation in a non-dimensional form, which is not possible in an experimental situation. However, whether it's an experimental or numerical, you can perform the experiment or simulation dimensionally also. Once you get the result, you can map it to a non-dimensional form. So finally, most of the experimental and numerical study present their results in non-dimensional form, because like for flow across a cylinder, if you are doing a experimental or a computational study at a Reynolds number of 100, you can claim that your result is applicable for wide range of fluids and for wide range of diameter of the cylinder, as and for wide range of free stream velocities. However, the combination of this thermophysical property of the fluid, the diameter of the cylinder, and the velocity scale, their combination should be such that it should lead to the constant value of the governing parameter, such as Reynolds number is to 100 in case of flow across a circular cylinder. So, whenever we do a study, we want to do a study with least of effort. So, as I mentioned earlier, rather than varying the thermophysical property, the diameter, and the velocity scale, which involves 4 different input parameters, we want to reduce our effort by varying only one parameter, which is the Reynolds number, and then That's one aspect of the study where we want to make our effort, reduce our effort. Secondly, we want to claim that our result is applicable for much wider range of situations. When I say wider range of situations, I mean it's applicable for, let us suppose, even if you do experiment or simulation for air, you can claim that results are applicable for water also, provided that you take the combination of the diameter of the cylinder and the free stream velocity such that it corresponds to a constant governing parameter value that is corresponding to Reynolds number of 100 for flow across the cylinder. So both geometrical parameters as well as the governing parameters, they are presented in a non-dimensional form. So now I'll present the non-dimensional governing parameters and non-dimensional engineering parameters. The non-dimensional parameters, which we commonly used in fluid mechanics, is Reynolds number. Prandtl number is a non-dimensional governing parameter which comes for force convection. Grashof number is a non-dimensional governing parameter which comes when you study natural convection. Richards number appears in the study of mixed convection, whereas this Weber number and Froude number appear if you study multi-phase flow. This Reynolds number corresponds to the ratio of the inertia force to the viscous force. This Prandtl number is the ratio of the kinematic force with thermal diffusivity. This Grashof number is the ratio of the Bouncy force to the viscous force. This Richards number is expressed as Grashof number divided by RE square. This Weber number corresponds to the ratio of the inertia force to the surface tension force. And the Froude number is the ratio of the inertia force to the gravity force. So these are the various non-dimensional input parameter or a governing parameter that comes in a problem. If it's a pure fluid flow problem, for most of the problem you have a Reynolds number. If it also involves heat transfer, then you find Prandtl number for force convection, Grashof number for natural, and Richardson number for mixed convection. All these are for single phase flow. If it's a multi-phase flow, then you encounter these two additional parameters, Weber number and Froude number. So these are the non-dimensional input or governing parameters. Now the non-dimensional engineering parameters are shown here. The skin friction coefficient is a non-dimensional representation of wall shear stress, which is commonly studied for internal flow like flow in a pipe. This friction factor is a non-dimensional representation of pressure gradient for internal flow such as in pipe. This drag coefficient is a non-dimensional representation of drag force, which comes into picture in external flow like flowing across a car or an airplane. Similarly, lift force also comes into importance for an external flow problem. The Strouhal number corresponds to a non-dimensional representation of the frequency of a periodic flow. Like for flow across a cylinder, there is a periodic flow corresponding to the vortex shedding phenomena, and the frequency of the vortex shedding is represented in a non-dimensional form by a Strouhal number. Nusselt number is a non-dimensional parameter which appears in heat transfer. For a constant wall temperature, it represents a non-dimensional representation of rate of heat transfer. For constant wall temperature, for constant heat flux, it represents a non-dimensional representation of the non-dimensional wall temperature. So these are the non-dimensional governing, and these are the non-dimensional engineering parameter. This is input parameter, this is output parameter. With this, I have come to the end of this lecture, and the details of this lecture can be found in the chapter 3 of this book. Thank you for your attention.